Now that we have studied our discrete random variables in quite some detail, our attention must now turn to our continuous random variables. Now, we've defined continuous random variables, we've sort of given examples of continuous random variables, but we haven't really studied them in depth. Well, we're about to fix that right now. And now there's several ways I can sort of give you the idea or the motivation for this. I think what I'm going to do is to start with a probability line chart. So remember these probability line charts? You know, where you have your horizontal axis, that's your x-axis, and then you had like the possible values of x. So I'm just going to say x1, x2, x3, x4, dot, 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 xn. So we have, so again, this is the way I'm writing this, the fact that I'm kind of listing these x values, that implies that I'm dealing with a discrete random variable. And the probability line chart is where, so the height of the line segment that we would draw would correspond to the probability. So let me just do my vertical axis here, and then if we use these kinds of charts to represent the PDF, so I'm going to use that notation. Now, instead of drawing an actual line, I'm just going to put a dot to represent the probability. So instead of actually drawing a line segment, I'm just going to put a dot here, and then maybe here. So it's like a probability line chart without the lines. So maybe we could call it a probability dot chart. Hey, we might just have coined something. And then maybe something like this, right? Right? So again, each height here corresponds to the probability that this value of x will occur, right? Now remember, with a continuous random variable, we're saying that all possible values of x in an interval now are part of the sample space. So it's not just the isolated discrete x values anymore, but now we're saying every value of x in the interval is a possibility. So if every value of x here is a probability, then instead of just having a few isolated dots, right? I mean, now it could be many, right? Because your n could be very big, but they would still be isolated. But now, as far as if our random variable is continuous, let's try to see what this picture would look like. I'd still put my little f of x on the vertical axis. I'm still going to represent my sample space here, but now instead of listing these isolated points, now I'm just going to say there's like an interval, like from A to B, and now I'm saying all the values of x in this interval are possible. So let's say we start with x equals A, and then I put a dot there. Then where would the next one be? Well, because we're now dealing with an interval, there is no next number, right? Now, what I could sort of simulate it is, let's say we made these intervals very, very small, like super, super small. Just push the x values together. And then what that would do is, that would put our probability dots closer and closer together. So I would have a dot here, and then a next one, and so forth. And notice I'm not lifting my thing off, but what I'm doing now is essentially tracing out a curve. And the height of that curve corresponds to, again, these kinds of probabilities, right? But the thing is, what we end up having with, quite possibly, is a nice continuous function instead of a bunch of isolated dots, right? And when we now think of it as a nice continuous function, since we can't distinguish between, like say one x value and the next one, the question now becomes, what is the probability that my random variable is in some interval, right? So since I can't There's like there is no gap between them. I can't say what is the probability that my random variable is equal to a specific number, right? Because I can't measure it that precisely to isolate just one number, right? But what I can do, I can then look at an interval. So I could say, what is the probability that my random variable is in this interval? And let's say the interval here is from x0 to x1. Again, where every real number is possible. And what I could associate with this interval, like we do in calculus, is an area under the curve. So if I do this, I could then say the probability that my random variable is in this interval corresponds to this area under my, I guess we should still call it a PDF, and that's exactly what we do. So this is still our PDF, but now the question shifts to, instead of saying what is the likelihood that a specific x value will occur, we're now going to say what is the likelihood that my random variable will be in a certain interval, right? And that's essentially, that this is kind of an intuitive way of how we can go from a discrete random variable to a continuous one. Essentially what we do is fill in all those gaps with a function. Now, the function might be continuous, it might be piecewise continuous, it might be differentiable at certain points, and when we're going to look at certain properties here in a bit, but in general, that's how I wanted you to see this connection between the discrete and the continuous, right? And I guess another thing, I won't really go into a lot of detail with this because I want to focus on the probability side, but let me just say this. This is the same concept, or in terms of a relationship, it's the same relationship between Riemann sums and a definite integral, right? So we know that Riemann sums, we approximate area using rectangles, right? Which again, we could associate with these heights. We could put a rectangle at this height and another rectangle at this height. But as our delta x gets very, very small, as we squish the possible x values together to where we can't really say where there's a gap between them, now there's no gap between them. And again, it's the same kind of limiting process that takes us from a Riemann sum to a definite integral. So a different way that you can sort of think about it. All right. So let's formalize this idea with a couple definitions, and of course, we want to do some examples of this because now we get to do calculus. I mean, how exciting is that? So let x be a continuous random variable. Again, we can use our RV abbreviation. The probability distribution, so the probability distribution or probability density function, so either distribution or density. Let me write it like this. The probability distribution function or probability density function. Again, we abbreviate it the same way, PDF, right? Of x is a function, right? And again, we denote it the same way, little f of x, such that for any two real numbers and I'm just going to call it A and B, with the assumption that A is less than or equal to B. In pretty much all cases it will be less than, but there's a a theoretical reason why we use the closed interval as opposed to the open interval. But so for any pair of real numbers a and b where a is less than or equal to b, this is how we define the probability. So now the probability that our random variable is in this interval, right? So between a and b, right? Well, we're now going to define it as the integral from a to b of f of x dx, right? And again, so the way we can interpret this, let me actually write this in blue since I have the area there in blue. So this is identical to saying that the probability that my continuous random variable is in a certain interval is equivalent to the area, right, bounded by this function, our PDF, right, and our x-axis, right? So, and the x-axis for all values of x, all real values of x in this interval. Oh, my curvy x. There we go, right? So now we're going to associate probabilities with areas, right? All right. So, so obviously, what we would want to do, and I mean, this is something that actually, you might think that now that we're getting into like the calculus stuff, that it might be slow goings and it's going to be really difficult. Actually, not. It's not, because what we're going to try to do is to build an analogy between all the properties and all the definitions and all the probabilities that we know for the discrete, right? All we have to do is build the analogy for the continuous and take a lot of what we've already developed and just translate it into the language of calculus. So instead of seeing a sum, right, now we're going to see integrals, right? So just to give you an idea, again, cumulative probabilities in the discrete case was a sum. Probabilities here for the continuous case will be an integral. In the discrete case, expected values was a sum. Now expected values will be an integral, and so on, right? So we're actually going to be able to kind of ramp up and get a lot of the basics just by building that analogy, right? So let's start by just stating formally what conditions, right? What conditions must our PDF satisfy? It certainly just can't be any old function, because remember, it still represents a probability, and there's still axioms of probability that we have to live by, right? So let's say this. So for f of x to be a legitimate PDF, the same kind of question that we now know how to answer for the discrete, it must satisfy it. So our PDF, so this function, it must satisfy. I don't know if I'm too excited, I just can't write. So it must satisfy the following conditions. Right. So in other words, we can't just pick any old function and call it a PDF and call it a day. No. If you think back, the two properties that our PDF in the discrete case had to satisfy: one, all the function values, whether they were in a table or in a graph or in an actual function, an algebraic function, they had to be positive. So for sure, we need that one as well. So our our PDF, right? I keep saying continuous because we don't know if it's continuous, right? But our PDF has to be a function that's greater than, or or equal to 0 for all x, right? Not just some, but for all x values, right? And the other property is, well, think about what we had said. One of the things we always have to check to see if something is a valid or a legitimate PDF, we have to make sure that when we summed up all those probabilities, then they had to be equal to 1, right? So that total probability, it had to be 1 then, it has to be 1 now. So what would that mean? Well, we're saying that we're using area, right? We're using area to represent probability. So what we're saying is then the total area under our PDF better be equal to 1, right? For all values of x, right? So, well, if x can be, in theory, any real number, all values of x, that would extend from negative infinity to positive infinity. So then we get this thing that are lovely improper integrals from Calc 2, right? So if we were to integrate this function over all possible values of x, right, it has to give me 1. If I don't get a 1, then it is not a valid PDF, right? So again, what this is saying, let me put my analogy here in blue. The area under the entire graph, right, must be 1, right? So what that means now, again, we know what it means for a function to be positive. Like when you think of the graph of a positive function, it always lies above the, well, the greater than or equal to meaning that it could touch. But for the most part, for us, it's going to be above the horizontal axis. And then we're saying that the entire area under that function has to be equal to 1. So graphically, this is what we're saying. Now, and we're still using our horizontal axis to represent the sample space. So now if I say, let's say my sample space extends from negative to positive infinity, and I have some graph that looks like this, right, over the entire line, then what it means, that entire area must be equal to 1, right? Everything there, right? So when you think about it, when you think about all those area problems that we've done in, let's say, in calculus, right? I think very few of them came out to 1, right? So again, it just shows that not any function can be a PDF, but we know what to look for, right? And let me just say one more thing about the improper integral. Yes, we will have to work with some improper integrals, but there are some, in fact, there are a lot of PDFs that we'll work with where the graph is only positive for, let's say, over a finite interval. So maybe the sample space doesn't extend from negative infinity to infinity. Maybe it only extends from like 0 to 10. And then you're working with proper integrals as opposed to improper integrals. But right, all those details to come. All right. So let's do an example of this. I know you're dying to see what does this even look like, right? So let's do an example. All right, so let's say x. So this example won't be like any kind of story problem. It's just a matter of us getting used to again, what things look like, what questions are going to be asked, what steps are involved in finding the solution. So let's say x is a continuous random variable with, let me state the sample space. So I'll go ahead and use my S. And let's say it's a set of all values of x where x goes from 0 to 2, right? So let's say it's something like that. So that's my sample space. Now let's write down what the PDF tends to look like, right? So with PDF, so f of x, and these tend to be piecewise functions, right? So it's this function. Let's say it's k x squared when x is in this interval. So x is between 0 and 2, and then let's say it's 0 elsewhere. So 0 otherwise. Right? You see this a lot when you're working with the continuous random variables. Now you get an interval, no longer a list, right? So we're not thinking of this as like 0, 1, and 2. No, this is like 0 and 0.05 and 1.7893 and so forth, and the square root of 2 and the square root of 3. All those numbers are in here, right? Right? Again, we can't list them, right? So the first question that we're going to ask is, well, what is k, right? So remember those questions back when we were doing discrete, seems like ages ago now, but no, just a few weeks ago. But where you had to figure out what the constant is, right? Well, let's do that in our question 1 using this PDF. So let's just make it simple. Find what k is, right? Find what k is. Well, what we know is that when we integrate from negative infinity to positive infinity of our PDF, right, we know that has to be equal to 1, right? But in this case, we really don't need to go from negative infinity to positive infinity because the sample space is the interval from 0 to 2. Now, we we have a basic idea of what the graph of x squared is going to look like. I don't know what the constant is, right? So we won't be able to make it too detailed of a sketch, but we can kind of sketch this piecewise function, right? So let's say this is our entire real line, right? And of course, then let's say 0 is in the middle. Well, it says that the actual PDF, our probability distribution function, is 0 when x is less than 0. So it would be, in fact, let me sketch it in a different color so we can identify. So this would be the part of the function, right? It's going to be 0 when x is less than 0. And then when x is between 0 and 2, well, it's going to have this kind of parabolic shape. It's going to be a portion of the parabola, not the full parabola, right? But it's going to go up, kind of like that. And then once you get to 2, let me mark off 2 here. Then as soon as you get to 2, you're going to have this jump discontinuity, and it's going to go back down to 0. So then it just kind of, zeroes out again, right? So even though the negative infinity to positive infinity is a part of the definition because we have to allow for all real values of x, in this particular case, because our sample space only consists of values of x between 0 and 2, we can ignore the interval from negative infinity to 0 and then the interval from 2 to infinity. And when I say ignore, this is what I mean, right? Using the properties of integrals, right? We can break this up actually into 3 separate integrals. We could say go from negative infinity up to 0, right? So we can split this to go from negative infinity up to 0, and then I'm just going to write everything back down. Oh, actually, let me write it like this. So we would integrate the function from negative infinity to 0, and then we would add to that the integral from 0 to 2, again, of our function, and then finally from 2 to infinity of f of x dx, right? And that has to be equal to 1, right? So I'm just going back to the name of the function. But on this interval from negative infinity to 0, the function is equal to 0, right? So there's no area. Look, there's no area under this graph because the graph lies entirely on the horizontal axis, right? So this part here is 0. Same argument for this one, right? From 2 to infinity, because of how the PDF is defined, again, there is 0 area under the graph of this function between the graph and the horizontal axis. So this is 0. So the only interval over which the function has positive area is the interval from 0 to 2. So then I'll plug it in, and then I'll go back and I write the actual function, the k times x squared dx. And again, that has to be equal to 1. So this is what I mean by ignore. You can't really see my air quotes, but I'm doing it. Ignore is that the function is 0. We're not ignoring it per se, but because the function value is 0, the area is going to be 0 over this interval, negative infinity to 0, and then 2 to infinity. So this is really the equation that we need to focus on for this particular example. All right. So let's go ahead and compute this. Let's try to figure out what k is. What makes this a valid PDF, right? Well, we have the property of integrals that allows us to take out the constant, so I can factor out the k, and then I have the integral from 0 to 2 of x squared dx, and then that has to be equal to 1. And then, yeah, so this is our basic power rule antiderivative. So k times, and then this is 1/3 x cubed going from 0 to 2, right? And we still have to show all our, antiderivative. It's part of our procedure. The fundamental theorem of calculus is part of the procedure. So let's evaluate this. So I have k times. At the upper limit, I have 8 over 3. At the lower limit, I have 0. Right? And again, that has to be equal to 1. So what we have on the left side is that 8 over 3 times k is equal to 1. So therefore, k has to be 3 over 8. Right? And that's the constant that makes this a valid PDF. Right? We got the positive part because of the x squared. Right? Well, technically, we can't really say that because we didn't know what the k was, right? But, we have essentially a part of a parabola that's opening up, again, assuming that k was positive, but we just didn't know what the specific value of k is. Now we know what it is, and it is 3/8. So let's restate the complete PDF now, right? Let's restate our PDF. Right? So now it's 3/8 of x squared whenever x is between 0 and 2, and then it is 0 otherwise, right? All right, so now we have the PDF. Let's actually compute a probability. Suppose I want to know the probability that my x is between 1/2 and 1, right? I know, for instance, if I were to integrate from 0 to 2, for this function, I would get a 1. That would be my total probability. So x has to be somewhere between 0 and 2. But what now, if I wanted to know what is the probability if x is between like 1/2 and 1, right? So again, let me do another sketch. And I'm only going to sketch the part of the over the part of the interval where the function is positive. So now it looks like, again, it has the same kind of shape because it's a parabolic function. And now I want to know what is the probability. So this would be 1, and let's say this is 1/2. I want to know what is the probability that my x is in this interval. So then I'm going to associate it with this area, right? Now, there's something that when we were studying the discrete random variables that we had to be very, very careful as to whether the endpoints were included or not. You know, that we distinguished, rightly so, between less than and less than or equal to, or greater than and greater than or equal to. But if you kind of think about this, right, from an area standpoint, if I want to find this probability where x is greater than or equal to 1/2 but less than or equal to 1, this is basically saying that the line segments at x equals 1 and x equals 1/2 are included. In fact, let me take this off, and I'm going to draw this a little bit bigger to really emphasize the point here. All right. So I'm just going to sketch this one the way what these inequalities are implying. So when I have the equal sign on at each endpoint, it is implying that the endpoints are included. So I'm just going to include that border as a solid line there, and this border as a solid line there. And again, we're looking at the area from this vertical line segment to this vertical line segment under the curve, right? But that area would still be the same whether or not I include the endpoints. So in other words, what if I just did this, right? The blue area, which I didn't draw, I'm about to draw now, is still the same, right? It's still the same. And the same thing would happen if I took out both of the those little line segments, right? My blue area wouldn't change. And the reason is because the area of a line is 0. It has no width. So whether or not I include the endpoints, it's not going to change the area under the curve. Therefore, it won't change the probability. So in a nutshell, here are 4 other probability statements that are identical to this and the way we would compute it, right? So we could have where this endpoint was removed and this one is included, or we could have it switched where the x equals 1/2 is included, but then the x equals 1 is not. So let's do the 1/2 less than or equal to x less than 1. Or both could be excluded, right? It doesn't affect the area in blue, right? So all of these now, we're like, hey, all the things that we had to be so careful of in the discrete case, do we go down? Do we not go down? How do we, what's included, what's not? Well, because the area of a line, in fact, let me write that, the area of a line is 0, it doesn't contribute anything to the area. Right? So whether I include both or only one or neither of them, my calculation is still the same. And what is that calculation? Well, take your PDF and integrate it from x equals 1/2 to x equals 1, right? So our probability now is going to be this integral. So from 1/2 to 1, and we integrate our PDF. So 3/8 x squared dx. And again, we need our power rule. So the power rule for this gives me 1/8 x cubed. And again, we're going to use our fundamental theorem. And so at the upper limit, we get 1/8. At the lower limit, we have 1/8 times another 1/8. So that's 1/64. Common denominator 64, so that's 8/64 minus 1/64, and that probability is 7/64. In some sense, I prefer doing the continuous distributions and probabilities because I don't have to do any crazy addition. I don't have to add up all these terms. Like you said, I don't even have to worry about whether endpoints are included or not. I just know that if I want the probability that my random variable is in some interval, then I have to evaluate some definite integral, right? So I think that's certainly a good starting point, and hopefully the transition kind of makes sense. If not, maybe re-watch the video again, and then just get excited as I am to be able to use calculus to answer these questions, right? And let's make that excitement carry over into the next video. See you then.